So we're going to talk a little bit about atoms. I have some videos to kind of break it up, some of my favorite videos. Okay, atoms and elements. But clear back, it seems like forever ago, we said that matter can be classified as either pure substance or a mixture. If it's a pure substance, it's either an element or a compound. You can go back and forth between elements and compounds by chemical reaction. So of course, elements, if you have a chunk of matter, it's an element, it means that all atoms are the same. Okay, plus or minus. Okay. So if you have an atom, you cannot, with an ordinary mean, break it down any farther and retain its chemical properties. So you can do some sort of nuclear fission. Fusion is putting together, fission is breaking apart. So you can split an atom, but that's not ordinary chemical reaction. So elements, you kind of got an idea what elements are. Here's a table of elements over here, and we'll be kind of talking about what makes them similar, okay, what makes them unique, what for a given box, what these numbers mean, okay. Here's a picture of copper. So all of those atoms would be copper atoms, and it's really hard to get a nice straight picture of an atom because it's really small. The light you use light has a certain wavelength to hit the atom with. It goes through the atom. So a single atom, not a collection of atoms. But this actually is about as close as we can kind of get to get a rough sense of the atoms. I think these are copper atoms, taking with probably some sort of scanning electron tunneling microscope. This actually doesn't animate for us, but if I were going to animate it, it just would give us our first sense of what you probably already know about an atom. We need to talk about the pieces of an atom. So atoms of the different elements have this in common, that they have a hard nucleus. It's like a Tootsie Pop, kind of the chocolate thing in the middle. Okay, it has what we call a nucleus. You can maybe see kind of the red and the green. Those actually are protons and neutrons in the nucleus of an atom. So we have protons is a letter P with a plus. Neutrons is a letter N with a 0 because they're neutrally charged. So this would be my nucleus. And then we have electrons out here. And on this, if I were to animate it, we see the most motion of any given atom is going to be in its electron, creating what we call an electron cloud. It's just so cool. Because anytime you see a picture nowadays of an atom, it looks like there are a gazillion electrons there, but actually we really don't know where the electrons are at any given time and how much energy they have around a given atom. So they're just kind of create this kind of probability cloud. All right. So I brought, is this where I want to do it? Yeah, I brought you, dun dun dun, can't have too many periodic tables. They are your friend. I mean, elements are so cool. I have a friend that knows, what I teach and what I love, and she said that in a recent business magazine that the science and the business of elements is where it's at. So I'll have to see if I can find that article. Sometimes I'm going to show you a video of a song that has all the elements in it. Maybe you've seen it. It's kind of based off of Tom Werner. Yeah. But anyway, they talk about the new elements. So can you compare what I gave you to this one? What's different?
There's no names. There's no names.
Well, that's on purpose, yeah. I meant like which elements are not listed up there. There's no names. That's a good point, Kelly. So this is the periodic table. The reason I give this to students is this is the one that you'll have on your test. Well, you can't go mark it up and bring it to take on your test. Right. But I will give you a clean one of these on your test. So you can kind of start to get yourself familiar with it. This is the same one that's like at the back of your, like this, it's the same one. Plus or minus, because this one has some gaps, like that periodic table. So yeah, you can tell the difference. They're down here, aren't they?
Like 1, 12, 1, 13, 1, 14, 1, 15, 1, 16, 1, 17.
So these are all filled out?
Mm-hmm. And 118.
Yeah. So this was like a big, hairy, exciting time, okay? These UUs actually, they just mean they're kind of in transition. The thing about, you guys are probably a little bit familiar with the periodic table. That number, that 111, 112, 113, 114, 15, 116, 17, 118, that is the number actually of protons in the nucleus of an element, or excuse me, of an atom, that type of element, okay? So, and protons and neutrons are what give mass to an atom. So these get heavier and heavier. And here's the deal. These are anything on this table that has kind of you see the font is, the font is kind of an open font. Those are synthetic. Those are man-made. Those don't naturally occur. They might have existed at some point on our planet, but their decay, their half-life is such that they don't exist anymore. So anyway, yep, so these are synthetic, and so what you gotta do is try to, for this 118, you have to successfully get 118 protons and the right number of neutrons to coexist in an atom, and the right number of electrons to coexist for a certain amount of time before they can go ahead and say it's stable enough to be an element. That's a little bit about that. So you are going to need to or want to know some elements, and I have a slide coming up that you're going to need to know, like what's the symbol, this one gets all this, what's the symbol for, what's up there? What's the symbol for silver?
AU.
AU. Wait, AG.
AG.
Oh, AG. See, I did it.
Sorry.
Yeah, AU is gold. I get those two mixed up. Why did they? Here's another common one. Okay, see what's up here. Okay, what's the symbol for magnesium? Mg. What's the symbol for manganese? Mn. I get those two too. So anyway, so you'll get to kind of, but like the slide says, if you have two letters like cobalt, it has to be a capital C and a lowercase o. That's a good example because I bet you guys might tell me that this is carbon monoxide and this is the element cobalt. So it is case sensitive. It does matter. It's been a few years ago, but for whatever reason, I had a student and a good student that just would always like sodium was that to them, and I do not know why. But anyway, so the second letter is lowercase. So here is my first of maybe 2 videos today. PB, and you're like, well, where did that come from? So actually, you can see that it came from Plumbum. Oh, I've referred, so, right? So I don't know, there's a reason for all of that. And this still isn't the one to memorize.
Oh.
This is the one to memorize, okay? So that sheet I gave you, the one you can't have too many periodic tables, so just put it under your pillow, okay? What you could do if you wanted to is, now, atomic number, we're gonna talk about some terms. And I want you to know that atomic number is the number of protons.
Does that mean 1, 3, 4?
What's that?
Oh.
So the atomic number, and it's the whole number in your box. Yes, ma'am.
Why is hydrogen on both sides of the table?
A good question. I'll say that in just a minute. Whole number. Okay, so for each box, you have a whole number and a decimal number. The whole number is the number of protons. The decimal number actually is how much that atom weighs. An average, what we call an average atomic weight in atomic mass units. Good catch. So the deal with hydrogen, you only see it here, listed once here, but you see it listed twice here, is because we're going to see, and maybe you kind of remember if you've studied this, the way the periodic table is organized is that with regard to the columns, what we call groups, that is similar character properties, chemical properties. They behave similarly.
Mm-hmm.
So I just do that to kind of show you that sometimes hydrogen can behave like this column, and sometimes hydrogen can behave like this column. So it's kind of got a split personality. So any questions about, what I started to say is like 1 through 20. So you take hydrogen through what's 20?
It's
Yeah, hydrogen through calcium. So all of those you need to know, be able to, and there's no specific test question about that. I do that for my intro Gen Chem students. This is not intro Gen Chem. Okay, so you're just going to kind of incorporate that knowledge when you work problems. So because the periodic table you get for your test does not have the elements names on it. Okay, then we skip a few, we go to 24, so you get the idea. Okay, 92, is that? Yeah, 92 is uranium, which I thought was kind of cool. 92 actually is the last one before you hit all synthetic. So, and we'll be talking more about this, but like the video said, could you see where you go from barium 56 to, then when you get to 57, that's lanthanum, and then to get to the 58, you have to go all of these guys. These are called the lanthanum series. And then after lutetium, then you go back, that's 71, you go back up to hafnium. Yeah, so we'll talk more about that. It has to do with how the electrons are being added. That kind of the lanthanide and actinide series. Okay, what else we got? Oh, so also kind of incorporate in your knowledge and your learning how you handle elements. There are 7 elements. Now this would be specific to Earth's general temperature and pressure, or atmospheric pressure and temperature, bless you. But there are 7 elements that you will not see. They have a buddy. They're what we say diatomic. And these are the 7 diatomic elements. I'll write down at the bottom how I remembered it years ago. I think these are listed by maybe increasing atomic number, but I remembered it. It's the German name. I don't know if there is such a German name, but Hofbernickel. So Hofbernickel. So H-O-F, B-R, actually that's one element, nickel. So N-I, and for the coal, I go C-L. So actually I've got 7 elements up there. I'm going to put little subscript 2 because we're going to talk about how we use formulas to represent molecules. So there's a 2 there, a 2 there, a 2 there, 2 there, 2 there, 2 there, 2 there. I used to have a laminated card that said Hofbernickel. I have no idea why. But it's interesting what you keep, what you remember. So this is to say, like, we're starting, if we do some sort of chemical reaction, like just simply, if we're going to take water, and I think we already looked at this before, you can take water and you can run electricity through it. And what's going to break down into hydrogen and oxygen, but actually it's not just H and O, it's H2 and O2. Okay, so I know it's not balanced, but anyway, you get the idea. Not all equations have to be balanced, but you're never going to see just a regular hydrogen, it's H2. All right, so these are where those 7 diatomic elements are on the periodic table. Periodic table. Okay. So, yeah. Okay. So, Dalton, who was colorblind, I heard that on a documentary a while back, but came up with several statements about an atom. Now, granted that he was not the first to come up with the concept of an atom, but he came up with what's called Dalton's atomic theory. So the way this is, speaking of colorblind, I hope you're not colorblind. I hope you guys can see the blue on the slide. I don't know if it shows up on your notes. Yeah, it doesn't really. So if you want to kind of put parentheses around which are indivisible and indestructible, those were part of Dalton's original theory that actually, as it turns out, are not exactly right. Talked about nuclear fission, okay, and atoms can be destroyed. They can be split, but that's, he didn't know about that. All right, again, a little bit of blue there. So Dalton, years ago, also said that atoms of the same element are identical in chemical properties and mass, okay? He went on to say that if you have atoms of different elements will have different masses and their properties will be different. So that's all true. The thing, and we're going to talk either today or Wednesday about the idea of, I think we're going to pick on copper, although there's a lot of them that do this, but there are various forms of copper, Copper is atomic number 29, so you know all copper atoms have 29 protons. But the number of neutrons in the nucleus might be different. And if they're different, even though it has 29 protons, their masses of those atoms of copper are going to be different. We call those isotopes. Okay. He also said, and this is really pretty cool for that time. I just think science is awesome, how it builds, and we all keep building on each other. But he said that you take atoms and you put atoms together in a repeating unit called a compound. We use formulas for those repeating units. But he said that the relative numbers of atoms that are in that repeating unit are relatively small whole numbers. And if you know much about biomolecules, DNA, RNA strands, you know that when you go to write the chemical formula, those numbers are not very small. So that's okay. This one's a little different. I have red here, and this was actually, I added this to his original statement to make it true, and it kind of goes back to his first statement, that if we say that atoms are neither created nor destroyed, we can go ahead and say that if we add to it what I've said before, as long as the process that you're looking at is an ordinary process. Ordinary chemical process versus some sort of nuclear process. All right. Okay, so there's a lot of, I teach physical science, and it's fun seeing how kind of chemistry, astronomy, meteorology, and kind of all fit together. But in this universe, there's a conservation of a lot of things. There's conservation of energy, conservation of matter. Those are kind of the two biggies. But we can look at conservation of matter in several different ways. By the way, the conservation of matter we count on in the chem lab all the time to run our experiments. So atoms, as we're going to manipulate them, will neither be created nor destroyed. And atoms make up matter, so matter is neither created nor destroyed. Okay, and all matter has mass and occupies space, so all mass will be constant too. Under ordinary processes. Now, of course, some of us know the whole Einstein's E is equal to mc squared, where matter actually can be converted to energy, which is kind of a nuclear processing again. But that's not ordinary chemical physical processes. So I have a couple pictures here. One is, I don't know if any of you guys are into microbrewery sort of thing, or making your own beverage, but this just simply says that if you're going to make alcohol, you might start it out this way. This is your pre-beer. You have your sugar down there. You give it time. It creates gases. It creates alcohol. Okay. But the thing here is, if you were to weigh the before and weigh the after, they should be the same mass. Bottled up, nothing getting in, nothing getting out. It's just changing. The same atoms are there. They're just rearranged in different compounds. This is a similar thing where you kind of have an early battery and kind of a more used battery, that as your battery does its thing in providing electricity to your car, the mass that you start with will be equal to the mass that you end with. Okay. So we know that you can take elements and assemble elements to make compounds. And so that kind of gives us to this law of multiple proportions. I was thinking about this at my desk, and there are a lot of hydrocarbons. A hydrocarbon is just something that contains carbon and hydrogen. Okay, hydrocarbon. So according to this law, how do I say this? Carbon atoms weigh something, hydrogen atoms weigh something. So if we're going to make our various compounds with different numbers, set numbers of carbons and hydrogens, they would have kind of the same, there would be a common mass multiple of that related to that. That's how I think of it. And kind of related to this, we have a, looks like a copper 2 chloride. This is CuCl2-ish, what I was thinking. So that means that, what you're looking at is not a molecular compound. It is a compound. It's an ionic compound. And it's the ionic compounds in their solid state actually make this cool crystalline lattice structure. So if I were to isolate it, to chop it, to cleave it anywhere, which I can do that, you would expect that I would have the same proportion of copper and chlorine. All right, so here we go. I promise on your unit, we haven't talked much about what's on your Unit 1 exam. So Unit 1 exam, so today's Monday, you have one more lab, and the following week is your unit exam. Could be worse, you could be having it on Friday the 13th. But on your unit exam, I will ask you if you know your way around subatomic particles somehow. And actually, a homework that's due, I think it's due Wednesday. Part 8 homework? I don't know. What's that?
It's due Thursday.
Oh, thank you.
That was split between 2 days.
It's split between 2 days? Okay, thank you. Perfect. I kind of remember doing that. So, you have part 8 homework doing this, and it will be on your unit exam. I call it kind of discounting particles, okay? We look at an atom, you already have a sense of, we call this the nucleus. And outside, and within the nucleus, we have protons and neutrons, and outside the nucleus we have nuclei, we have electrons. I have a video to kind of give you a sense of size with regard to these. But these are the 3 particles that chemists worry about. Now, if you're a physicist, you have a few more particles, but we're not going there. These are fine for me. Okay, so you guys are familiar with scientific notation. So the nucleus would be about 10 to the negative 15 meters. Very small. That's why it gets hard to take a picture of an atom, because you can't have light bouncing off of that. The electron cloud, it depends. Well, the size of the nucleus and the size of the electron cloud obviously depends upon what element you're talking about. But you're talking ballpark, the electron cloud, and it's not necessarily spherical, is going to be about 10 to the negative 10 meters. Okay? But like the slide emphasizes, and if you're a visual person or however you want to think of this, when I look at these 3 subatomic particles, where they are, and this is electron, I said cloud. This nucleus has basically, for all essential purposes, all of the mass. Well, if the nucleus has all of the mass, then the electrons must be basically massless. And they are, for all intents and purposes. Again, chemists, as we are. So I'm going to play you this little video about kind of relative sizes of an atom. But it says if an atom could be expanded to the size of a football stadium, the whole atom, so that would be the edge of the electron cloud, then the nucleus would be the size of a blueberry. So the video I want to show you actually is a TED Talk on the subject. We had a BB and considered that the nucleus. Then we would actually put it in the middle of a 10-story building, and then on either side, the top of the building and the bottom of the building, that would be kind of the edge of your electron cloud for a typical atom. So yeah, this whole empty space thing, and there's like the scientist who kind of figured that out was kind of freaked out by it. Well, no kidding. Next, please. Okay. So you're going to need to know a few things about these subatomic particles. What do you need to know about the protons? They are positively charged, and actually the magnitude of the charge is equal to the magnitude charge of an electron. So they kind of cancel each other out, which is what we're counting on. They're found in the nucleus. There is an attractive force between the protons and the electrons. So I would put this in and put this in. So they want to be unlike, attracts unlike. Okay. So based upon that, then, if I add another proton in here, okay. Oh well, forget it. That's coming up. So all the mass is generally contained by these 2 subatomic particles. And you already have a sense of this because when you go over the periodic table and these red numbers are their atomic numbers, they're the number of protons. So if you want, and this is why alchemy kind of makes sense, If you want a silver atom, if you want a silver atom, all you got to do is get 47 protons in the nucleus of your atom. So you could take two of something that's lower and put them together. Okay, so it's all about the protons that define the atom. Neutrons have no charge. Okay, they're also found in the nucleus. And what I started to say a minute ago is, if I add another proton here, you figure now I have two that are the same charge, and these are actually going to fight each other. They're going to repel each other. So the presence of the neutrons kind of helps to join it all together, kind of dilutes the effect of otherwise protons that don't want to be near each other. I got 5 more minutes, people. And I slow down as people start packing up too. So, what was I saying? So the two things that give and I like the video we watched because it kind of emphasized just how dense the nucleus is. So the two things, protons and neutrons, give mass to the atom. Electrons are outside the nucleus in a cloud. They're negatively charged. When it comes to the whole volume of an atom, and I like the video too, because it kind of talked about how that's kind of crazy. The electrons are what gives size or volume to the atom. When it comes time for this atom to connect to another atom, we're going to see, this is my other nucleus, and here's my other electron cloud. We're going to see that actually it's the electrons, and to me this just totally makes sense. It's the electrons that kind of do the binding in order to bind to connect these two atoms. Here we have kind of a picture of an atom that we looked at before. Again, the two colors would be protons and neutrons and an electron cloud outside. That won't animate. Here's a nice handy little table that talks about the 3 subatomic particles that we're worried about. You see the charges I mentioned of the proton and electron are equal in magnitude, opposite in size. Sign. Over here, this column right here, we're going to introduce a new mass, not pounds, not kilograms, not ounces, but atomic mass units, or AMUs. And you can see relative mass. The electrons are what we say relatively massless, and these are the protons and neutrons. Okay, that's probably a good place to stop. So we'll pick up here and knock this out of the park on Wednesday and start parking. Sounds like cookies and watermelon tonight, I'm just saying.